So beginning in chapter 6, so this chapter deals with the normal distribution. And there's many things that we're going to investigate about a normal distribution. But what we want you to understand right off the bat is that it's called a normal distribution for a reason. The normal part is that this is something that happens basically on average. It becomes the norm when you do it enough times that it follows this distribution. So always kind of keep that in mind, as a normal distribution occurs many, many, many times in nature and in probability of things, as we're going to hopefully find out in our little ruler experiment, that it shows up there. And so just kind of keep that in mind. Okay. This normal distribution works with continuous variables, and they have what's called a bell-shaped. And it's either called a normal distribution or a bell-shaped. Sometimes it is also called a Gaussian, is the way that you pronounce that. But that's probably the least used name, and for a reason. Normally, and bell, way easier to say. So here is the mathematical formula for this. And what this does is this will generate a graph. So if you plug in values for x into this equation, where you have to have, so you have all this data, right? And from all this data, you have figured out what the population mean is and what the standard deviation. So you know those two values. This can differ depending on whatever your data is. So this could differ very much with our ruler experiment. What's the average distance it took somebody to grab? Right now it's looking like our average is right around 5 to 6 inches. So that would be our mean, and then we'd also have to calculate our population, or our standard deviation. So we'd use those numbers in there. And if we plugged in different x values, okay, think about your x and y, they would give us y's. And what this y would, when we started plotting these points, you would find make kind of a bell-shaped curve. Okay? The more x's that you plug in, the more points you'd get on the y-axis, and slowly you would develop something that is kind of bell-shaped. Okay, I know this is very, very bad right now, but that's what this equation gives us. The good news is that we don't have to use this by hand very often. Okay. Okay, so normal distributions. The shape and the position of the normal distribution curve depends on basically these two parameters, a mean and a standard deviation. Okay. Each normally distributed variable has its own normal distribution curve, and that depends on the values of the variable's mean and standard deviation. Give me 1 second, I got some. Okay, sorry. So what we're talking about here is that these are two different graphs, and they are both bell-shaped, but they're both differently shaped. The shape and the position of it all depends on two things. The mean, which will determine where basically that peak of the bell is, and the standard deviation will tell you which one, like the width of the bell. Okay, so we're going to look at two different ones. So this is what two graphs would look like if the means were different. If the means were different, but the standard deviations were exactly the same, your bells would look like this. They're just in different positions on the graph. But you notice that the overall shape of them is the same. If our means were different, but the standard deviations were also different, notice here the standard deviation of this blue graph, this blue curve, is bigger. It's a little bit more spread out. If you look at the distance between here, that's a little bit longer than the distance between here, right? So that's what the standard deviation does, is it determines how wide the graph is. The mean determines where it's located on the graph. Okay? I want to go back here just because, just a reminder, or pay attention again, that on here, the mean is the same. So it's located at the exact same position on the graph. Mean is different, mean's the same. Standard deviation is different, standard deviation is the same. So that's what it does. Okay. This next part, this is what you copied on page 303. So I'm going to go through these properties really quick. Normal distribution curve is bell-shaped. We talked about that. The mean, median, mode are equal. Okay, those are in the center. The normal distribution curve is unimodal, which means that you don't have basically a graph that goes like this, and then like this, and then like this, and then back up like that. You don't have a graph that has these all kinds of different peaks. Okay, it's just got one peak. It's unimodal. The curve is symmetrical about the mean, so the mean is usually always at the peak, and it should look the same on both sides. Mine is not. That's why this is not a very good bell shape. Now, what we want you to understand too is that in real life, you're not going to get this exactly perfect. Okay, you're going to get really close, but it may be just slightly off. So kind of keep that in mind. The curve is continuous. There aren't any, spots in it or anything like that. The curve never touches the x-axis, theoretically, no matter how far out it goes. So what we're talking about there is that when you draw that, okay, this never touches the x. Okay, that doesn't happen. Theoretically, okay, it may become so close that it looks like it does, but theoretically it doesn't. The total area under the curve is equal to 1, meaning it covers 100% of all possibilities. Okay? So this goes back to the empirical rule, which we already covered. One standard deviation away covers 68%. 2 standard deviations is 95%. And 3 standard deviations covers 99.7% of everything in there. All right, so that's the area under the curve. Understand that we are talking about the area that falls under. So if we were looking at 1 standard deviation, here's our mean, we'd be talking about this area in here. That's what we're talking about, that percent. If we go 2 standard deviations out, we get to 95. So that's what this shows right here. Notice that this 34.13, that's combined. So combined from here to here is approximately 68%. It's not exactly at 68.26, and we got some decimals cut off there, but approximately. Thing to keep in mind, this area right here is another 13.59. If you take that 13.59 and add it with this 13.59 and then add it to 68, you will get approximately 95%. So between this one and this one is approximately 95. And then if you go 3 standard deviations out, that's approximately 99.7. So that means all this area, if you colored in all this area underneath the curve, not that part, that all these values would be 99.7% of everything. Okay, there's obviously a little bit that goes out here, and that would be that other 0.3%. So what happens is we will be measuring different things, right? Right here we're measuring the amount of inches it takes before your reaction, and you close your fingers. And we're dealing with numbers anywhere from 0 to 12. We could be talking about people's shoe sizes. We could be talking about students' heights. Students' heights, we'd be using numbers anywhere from, theoretically 0 inches tall up to, who knows, our tallest person could be, 8 feet tall. And that's the scale then that we would be using. And because these scales, what we're talking about, on the x-axis, because this scale can be so different, we try to standardize it. And so standardizing it gives us a mean of 0 and a standard deviation of 1. So here's what we're talking about. It would be like drawing on a graph where 0 is your mean and your standard deviation is 1. Okay, 1 here. So this would be -1, and this would be +1. Okay, and then you could go 2 and 3 and so on and so on. So that's why we standardize it. So if we try to standardize everything, how do we turn our values into something standardized? The way that we do that is we use something called a z-score. The z-score, which we've already calculated in previous chapters, is whatever value we're looking at minus the mean divided by the standard deviation. And that gives us a value that we can use on the normal distribution. There it is symbolically. This chart on page 305, that is something for you to, you're not going to memorize it, it's just kind of something to go back and help you understand how to calculate these things that we'll be talking about in a bit. That is where I'm going to leave off on this video. I'm going to make another video about calculating the area underneath the curve, but I want to leave you alone with this one right now.